Thank you, everyone. So I'm going to start my presentation with a quick introduction to Cheyenne, the NCAR supercomputer at NCAR. So let's start with NCAR, and if you don't know, this is the iconic building of NCAR in Boulder, Colorado. If you have a deja vu, it's okay, because this building appeared in a Woody Allen movie called Sleeper. So if you have seen the movie, Woody Allen was escaping from that building, basically. And the supercomputer that we recently got is 5.34 petaflops, built by SGI, with Brodel processors and Mellanox EDR InfiniBand. And currently there are 5 MPI implementations installed on the cluster. And unfortunately, this cluster doesn't have GPUs yet, but NCAR recently bought a prototype for an extension to Cheyenne that has lots of GPUs, B100, for machine learning purposes. So I used as a benchmark 2 models. The first one, it's very famous. It's the Weather Research and Forecast Model, also called WRF, that is developed by NCAR. And very famous model, you probably know it, and it's parallel numerical mesoscale weather forecasting, and it's used for both research and operational environments. The good thing about WRF is that it's a community model, so it's open source, it's free, and everybody can contribute, and the support is centralized at NCAR. The model is mostly implemented in Fortran 90 with some part in C and Perl, and of course it uses MPI for inter-process communication. Okay, the charts that I'm going to show you about WRF have been ran by 2 interns that we had at NCAR this summer, Akira, Kyle, and Dixit Paddle. So for the test that I'm going to show you, they used 4 test cases, basically 2 different versions of CONUS with different resolution. Of course, the final resolution means more computation to do and more grid points, as you can see here. And is there a laser? No. Okay. Here you can see the total grid points. And the other one is Maria. It's even bigger. In Maria, it's the Hurricane Maria. That's where the name comes from. So let's start with the overall scaling. On the left, you can see a kind of for us it's very common, but for computer scientists it's kind of unusual because it's represented the other way around. So on the y-axis, we have the time step per second. So the higher, the better. More time step per second means that the code is running faster per second. On the x-axis, instead, we have the total grid points per core. So this is with more cores. This is with fewer cores. So in fact, if you have fewer cores, the time step per second is slower. You can see that except for pitch, all the others perform pretty much the same. Difference is on the kind of time that gets spent inside the application. So you can see, I think this is MPT, and you can see that the blue dots are basically the total, whereas initialization for the interns means the collectives that get issued at the beginning of the execution. It's not MPI init. It's the time required for the model to be initialized. Then there is in green the computation, and then there is this crosses, blue crosses as the writing output. So you can see that the computation scales pretty well, whereas the initialization and the I/O stays pretty much the same for MPT at least. All right, this is a pretty good slide that I would like to discuss with you. So again, this is another example just for computation time scaling. And as you can see, the scaling is pretty much linear for computing, at least, across all the models. The curious fact here is that Yellowstone, which is the previous supercomputer that NCAR has, performs better. And the reason is really simple. WRF is a memory-bound model. And memory on Yellowstone was faster, and the CPUs were faster, higher clock rate. This means that it's not that Cheyenne is not a great supercomputer, it's that the code of WRF must be redesigned to take advantage of the more cores instead of just switching, trying to get advantage of the faster memories, which is an exascale problem, I would say. Okay, so I asked the interns to run some tests with Mvapich. Unfortunately, MPI is a pretty recent installation on NCAR. We recently, in April, I think, when Panda visited NCAR for a conference, SCA conference, we started testing MPI on NCAR on Cheyenne, and we collaborated a little bit with DK Group. And we kind of tried several configurations that had been suggested by DK's group, but actually we couldn't get any huge difference in terms of initialization time, so collectives here on the left, and I/O. In fact, MPT is always almost always better, and this test case is CONUS, so it's the smaller test case. Whereas all the configurations we used for MPI perform pretty much the same for I/O on the right and initialization time on the left. Init time is collectives. How much time all the data that are needed gets distributed to all the processes. So it's broadcast or other all-to-all, this sort of stuff. I don't know exactly WRF's code very well, but it's mostly collectives. And this one, I think, is parallel I/O, MPI I/O. Are there any questions about this slide?
It's just curious that
broadcast operation or what?
Not sure. Probably broadcast. Definitely broadcast, but I'm not sure which others.
the numbers are a bit curious because it seems to go down until about 128 processes, then it goes flat, then shoots up. So it's just it's something we need to look at.
Yeah, the next test case is different. So this is Maria. It's kind of similar in terms of, incline, but where it basically skyrockets, but this is more dense. There are more data involved in this test case because it's a higher resolution. Yes?
A couple of questions. So is this one MPI rank per core?
No, I think it's 16 or 32.
Per core?
No, sorry, per node. Yeah.
Okay. And then the next question is how many ranks per node and how many cores are on the node?
So on each node there are 36 cores, physical, 72 logical. We never use the logical. They are activated, but we just decide to stick with the 36 at the most. And they usually run in power of 2. So the students, I think they run on 32, using 32 processes per node.
What is maximum number of nodes you have run WRF?
I'm sorry.
What is the maximum number of nodes you have run WRF? What is the maximum number of nodes?
On the machine?
Number of nodes I'm asking.
What is the last problems the job size you have?
So that looks like it'd be on 64 nodes. That's 22,048 maybe on the right hand side.
This is cores.
Yeah, I know. I'm dividing that by 32.
Yeah.
So is the right number 2,048 on the right hand side?
Yes. Oh, the right hand, you mean? Yes.
Well, of that chart you were looking at.
This one?
Yeah, so that bottom, the far right data points are at 2,048 cores. Is that's a question?
Yes.
Okay, so that would be 64 nodes then.
Yeah.
Okay.
I think if they didn't use 16. I'm not sure. I didn't run this test. So it should be 64 because they try to fill the nodes as much as possible. So it's 32, I think. The greatest test we can run, I think we have 2,000 nodes, something like that. So 2,000, I think. Something like that.
And what was the PPN process at that time? 2000?
The sorry?
2000?
Yeah, 2,000 nodes.
32 PPN?
36 at the most. Yeah. And we usually run on 32 just to make it power of 2. Any other questions? Comments?
One other question. So, this is a weak scaling problem or strong scaling problem?
Strong scaling problem.
Strong scaling, okay. So, which means that as the job size increases, the amount of data transfer should decrease.
Yes.
So, I think there's something wrong with the collective tuning, or it's not using the most optimal connectors because it shouldn't shoot up like that. I would expect some increase, but not so much. So it is something that we can definitely take a look at.
Yeah, I mean, I think the only MPI implementation that got really tuned is MPT, just because it's provided by SGI. Okay, there was a question there.
Just the IO, like WRF has a lot of options. So which option do you use for the IO?
No option, just the default.
Just the default. So
Yeah.
the core rank 0 is reading it and broadcasting it. Is that?
I think so. I think so. That they didn't say anything about any.
They didn't try peanuts if you have.
No.
I think if you know broadcast or whatever the type of call that may be used in it, you can actually just try just that call to run, across the 2,000 cores that you have. Sorry, you can just try that call in the 2,000 cores that you have. I think the jump, every time you have a jump, I think this is when you have a switch hop.
Okay.
So 512 is like 16 nodes,
Okay.
or depending on how the switch configuration is. So it may be a setup issue of SHARP or the collective offloads for in an pitch.
Okay.
Yeah, you should have a try.
Yeah, definitely we need to do some tuning, but anyways, it's just, I mean, for all the rest and other not regular MPI subroutine, it works really well. Okay, so now I'm much more familiar with this test case, so I will be much more, how can I say, meaningful in terms of answer that I can give you about this model, which is WRF-Hydro. So WRF-Hydro was originally designed as a model coupling framework to facilitate the coupling between WRF, which is an atmospheric weather model, and components of terrestrial hydrological models. So WRF-Hydro is both a standalone hydrological model, but it can also be used with a weather model. So originally it was strictly designed to work with WRF, but now it's kind of evolving over time to possess more additional attributes. WRF-Hydro is also a community-based model, and I stress a lot this fact because community-based model drive the decision that have basically have made during the past. An important aspect of WRF-Hydro that makes this code relevant is that it's the core for the new national weather model. So in the United States, if you want to know if there is an hazard or something like that, there is this national weather model managed by NOAA, and the core for hydrological hazards is basically WRF-Hydro. Let me show you a quick video about the flood we had in 2013 in Colorado. No, there is no audio. Okay. So down here there is Denver, and this is the whole front range, basically the beginning of the Rockies. And as you can see, these colors, these shades, are basically the water that stays on the soil while raining. And this is a pretty good simulation of what happened. Basically, the mountain came down and impacted Boulder and other areas on the front range. So this was a pretty good example of the importance of WRF-Hydro. Yes?
So how do you make these cool-looking videos?
There is a visualization software that they have, and it's not me, but there is a specific software for that. They hate it, but anyway, it looks good. All right, so if you were here the first day, I really encouraged MAP because that's what I used for improving the performance of the model. If you are familiar with MAP, you will know that blue means time spent in MPI functions, which doesn't necessarily means communication. The green is execution of something and can be floating point or other things. Usually floating point are represented also by this green mountain here in the second slice basically of the screen. And IO is brown, so this little thing here. I have to say, I started working with WRF-Hydro because the group that develops WRF-Hydro didn't have any software engineer, which can be weird, but it's reality. And they say, okay, can you do something for our code because it's Fortran, modern Fortran, basically. Sorry, it's Fortran 90. They want to shift to modern Fortran, and I kind of work with that. So I tried to help them, and I started profiling the code with map, and that's what I found. So basically, on 500 processes of Cheyenne, the model can do 2 advances, which basically means can produce 2 hours of outputs of water flowing in terms of simulated time. And for 32 processes, just to make sure that I was looking at the whole picture of the model couldn't even start the simulation. After the performance optimization by using the techniques explained by John the first day with cache, blocking, and other things, we managed to execute the model for 3 advances in this case in 238 seconds on 500 processes. But the good thing is that now we can run completely the model on 32 processes, and it's taking 18 minutes.
Any reason why you are significantly under-subscribing the node? The node can have like 36 or 32 processes. Why? So is it a memory-intensive factor?
I did that just to make sure that I was looking at the whole picture with map, because sometimes map, if you use lots of cores or processes, you don't see the lines, you don't see what's taking time very well. Whereas with 32, it's kind of more evident. And the good thing is that I want to stress here, the thing that I want to stress here is that this time here, the whole thing from here to here, is just for initialization, just to prepare the topology. There is a problem with the data structures, but hydrology model have this problem with river topology. And I'll show you a picture that will make this much more clear. But again, what I want to stress is that for a small number of cores, this model is bounded by the initialization time. Because when the model has been initialized with all the topology that has been built and so on, the execution is very quick. There is very little communication because we have just 32 processes running, and it goes really fast. On the other hand, when you have 500 processes and and just process 0 is running on disk, like in this case, you have a big problem with scalability between the iterations. So you have a shorter time spent during initialization, but a longer time between advances. And this is a big problem because they usually run 240 advances, so it takes a week to finish this execution. And the implementation I applied for the cache were just on initialization, so I didn't work on this in terms of caching, but I did work on this with a technique that uses overlapping and MPI. Okay, this is just to make sure that you understand why the hydrological model are weird. This is a map of the United States, as you can see, and about the rivers. Lots of the rivers are hairy, like they don't have any real source, like this. Little things like this that must be taken into account, but that actually when you build a topology have almost no effect in a certain way. They don't go anywhere, or they don't start anywhere. They just are there for rain or something like that, and there are many of them. So this makes the situation really unbalanced. It's not really that every river goes somewhere and comes from somewhere. Some just are there because that's the topology. So it's a very unbalanced problem as opposed to the weather model, which are really unbalanced in a certain way. Okay, so these are the ramps, basically. These have been a pretty big problem for me to improve, because when you see these ramps here, the blue one means that there is an imbalance. And this is mostly due to the nature of the problem and the data structure that they're using, which is not optimal. And this is an easy fix. We change the data structure, we write some code, and this will disappear. And there are also other solutions that we can do in the short term for example, using OpenMP. We have these big loops that have to scroll the whole list of rivers and sort the rivers to build the topology. We can do it with OpenMP. It's a pretty easy task. These are just few charts that show you the performance improvement on the initialization. So just using some cache blocking techniques, we managed to drop by 50% the wall time for a small number of cores, of course. Because otherwise, when we start using 128 cores, there is a plateau, of course, because everything gets dominated by the I/O and not by the initialization. This is just for the core hours. This is something that the manager love to see because we basically are saving money. Thanks to MAP and the optimization we developed, we are saving lots of money with compute hours. Now we can run with 32 cores, with 32 processes, and basically have almost the same Walltime as we used to have for as twice as much, basically. So we are saving half of the compute hours. Any questions so far? All right, now the difficult part, improving the I/O idle time. So process 0 in this configuration of WRF-Hydro, and it's the only one right now, is in charge of computing and dealing with the I/O. And this double duty on process 0 slows down the entire application because everybody must wait for process 0 to write on disk. There are 2.5 possible solutions. The first one is implementing parallel I/O, which might sound the perfect fit. Unfortunately, it's not super portable in terms of performance. If you have a supercomputer, you're fine, but this is a community model. They want this to run anywhere, on small clusters, on a computer, on whatever they have. So they kind of say, oh, you know, it's not super portable. I saw the performance of parallel net CDF and I don't like it. So I need to work a little bit more because in my opinion, this is the solution, but they don't like it. They said, oh, how about we create 2 groups to communicate? One for a group of processes that does I/O, and one of a group of processes that does computation. It's much more difficult to program because it's just parallel I/O but handwritten. But apparently they like this solution. I don't know how long it will take us to do this, but because this group is just paying my salary for a quarter of my time, so I have just 1 week a month, they say, what can you do with this time? And I say, okay, let's try this solution. Let's just try to overlap some communication with the I/O. So while process 0 is writing on disk, all the other processes can send the data at the same time, because right now it's very synchronous, the way it's implemented. And of course, you may know that if process 0 is not calling MPI, and we don't have actually a synchronous progress going on, there is no overlapping. So, just to make sure that we are speaking the same language, I'm pretty sure you're really well aware of this. But if you want asynchronous progress, you have 3 choices. The manual progress, which basically means you call MPI test once in a while, or MPI probe, or iProbe, or whatever. And basically calling MPI pokes the MPI engine and makes the progress basically happening. The second one, which apparently is the silver bullet, is thread-based progress, and there are 2 options. The polling-based approach, where the thread keeps calling the engine all the time, or the interrupt-based. So the thread is kind of sleeping and then waits for an event to get triggered by the card, basically. The third one is the offload, and it was really promising at the beginning, but it basically went nowhere, I think, with Quadrix. That was the cards, yeah. So, as I said, the winning model for the winning approach for asynchronous progress is basically a thread-based approach. The main problems are that first you need a thread-safe implementation of MPI, which is not a big deal, but still impacts a little bit the performance. And the main problem is actually the resource contention and the context switch of the thread. So you have always a thread running beside your process that pokes the MPI engine or stays there and gets activated when progress is needed. And this is bad for performance. And this is what I got in terms of performance of the 4 MPI implementations I tried. So this is a percentage improvement, meaning that the improvements between quotes, because 2 of the MPI implementation perform worse on the optimized implementation because they don't have a good progress, or they kind of pay a big penalty for the derived data type that I'm using. So
what optimization kit you are using?
I just used non-blocking MPI I send, MPI I receive while the process 0 was doing I/O. So I has to write a big matrix, for example, and why a slice of the 3D matrix, and why a slice of a 2D slide of the matrix is coming, process 0 is writing the one before. So there is kind of this mechanism that allows a little bit of overlap. As you can see, MPT performs the best, and we can reach 9% improvement for 512 cores. processes, sorry. MVAPIC does pretty well, never goes negative, which is good, but it reaches 2.25, so it's a little bit less, mostly because it has not been tuned at all in this case. For Intel and OpenMPI, it's totally negative or 0 at the best. So OpenMPI is probably the one that performs the worst, minus 9% performance improvement for 64 processes. This is just for 4 advances. Basically, if we can optimize this overlapping, this advantage comes for each advance. So the more advances is usually more time we save. But it's not always the case for several reasons. Any questions for this chart?
This is compared to their base time?
Yes.
Individual base time?
Yes. So you have the original version, you have the optimized version, you run it, and you see what happens. I haven't used any specific MPI asynchronous progress thread. It's just plain MPI as it comes. This is instead for 12 advances. Sorry if this slide is not pretty, but it was last minute slide basically. So for 12, so 3 times more advances, so more computation. With MVAPIC we can get 1.5% improvement, and we can get 5% improvement. This is always running on 512 processes. So in conclusion, MVAPIC looked promising, so we really want to have an MVAPIC, highly tuned MVAPIC implementation on Cheyenne. Overlapping computation and I/O represents a good non-solution for WRF-Hydro, because the solution is to fix the I/O. So it's not the cure, it's not the solution. It's something that I did just because they asked for a performance improvement for the I/O part of the model. I implemented lots of optimization for the initialization, but I wanted something also for the advantages, because they run 240 hours. So even if they can save 1 hour, that's fine. They are very happy. And I'm really looking forward to using MVAPIC 2X 2.3 because it has better synchronous progress. So thanks a lot for your attention.
Any questions? So what is the average size of messages, broadcast message in your WRF?
Word for WRF-Hydro?
Sorry?
You are asking about...
WRF. WRF.
Oh, the blue bar, you mean?
No, not WRF. What is the average message size?
Oh, they're big. 100 megabytes.
Okay.
Yeah.
So I have some ideas like we can discuss on.
Definitely. We got to the evening, yeah.
I have a question. What do you mean by, were you going to ask? Go ahead and ask. That's fine. What do you mean by a communication offload? You just pass through it.
So there are these 3 approaches, and communication offload means that the NIC takes care of everything. There is no...
And why? Yeah. So it's what I was thinking. So why is that a bad idea?
No, it's not a bad idea. It's a great idea sometimes, but it doesn't work that well. It's kind of slow, and it's kind of expensive. It's not
for the NIC to take care of it.
Yeah.
It's like the card that I was talking to you about with the FPGA on board. Like, couldn't you use the FPGA to accelerate some of what you're doing?
I think so, but apparently CPUs are faster.
I mean, if you burn an image to the FPGA that's specialized to doing that one thing, it's like a filter or whatever, or even the matrix manipulation multiplication that you're doing, you might get good results with it.
Definitely, but I think there is some hardware going on now for the tag matching.
I can answer that.
I'm not the expert.
So there is the Mellanox adapters have a technology called CodeDirect, which has been there for many years, which offloads collectives. So we have actually support for that. You can offload, but as Alejandro was telling, it doesn't happen very efficiently, the offload. So sometimes if you do a lot of offloads, in fact it gets slowed down compared to what you can do it in the host.
The embedded processors are not as fast as CPUs.
Yeah. So then the next one, what you are talking about, this new FPGAs, whatever is coming, those need to be evaluated properly, and especially the Mellanox latest ones don't have with InfiniBand. I think you are working with Ethernet adapters. Yeah, so they don't have those on the InfiniBand adapters yet. So there are a lot of these kind of trade-offs exist. Just offload doesn't mean that it is always good.
Yeah.
Okay, so you will see a lot of papers in the literature because depending on the CPU speed and the network speed, could be a lot of trade-offs. Whether you are doing one offload or 15 back-to-back offload. Sometimes the network gets choked or the adapter doesn't have enough resources. All of those kind of issues come up. We can discuss offline.
Okay. Yeah. Yes, quick question. If I understood correctly, you said you, for this progress thread, you implemented manually, you're not using the one from the MPI implementation.
I didn't do anything of that. I just said,
Okay.
I just basically brought the non-blocking and I just run MPI.
Okay.
I didn't use any mph_async_progress flags to have an helper thread that helps. I don't know about MPT. MPT has a pretty cryptic documentation in that sense. So I don't know what they're doing, but with some tests I can see that they have a pretty good asynchronous progress. I don't know how they do it for the two-sided.
Because I know OpenMPI has also an option to enable the progress thread where at the compile time and the configure, but I don't know if now it's enabled by default or not.
OpenMPI has the thread, but I think they pay lots of, the price there has been paid by derived types because I'm using derived data types to slice the metrics. So I think building and dealing with derived data types is kind of inefficient inside of an MPI. That's my guess.
Okay.
I haven't seen the code that does that, but it's not because they don't have overlap, but because they pay lots of overhead for other things. That's probably my guess.
Okay, thank you.